ठीक है. So last time we had done center of mass, है ना? We discussed how to calculate center of mass for continuous objects, and I gave you a list of the objects, ठीक है? List of the important center of masses, you can say, which you have to remember. ठीक है? So that is important, so you have to keep that in mind. ठीक है. So now let's move further. That is motion of center of mass. Okay, we have to now study the motion of center of mass. That what will be the motion of center of mass if objects, okay, if the system comprises of different parts, okay, it has different point objects and they are moving differently. So how will the center of mass be moving? Okay, so first of all, in this we are going to talk about point objects only. Okay, mostly there will be point objects only. Continuous objects motion of center of mass will be studied in rotational motion. Okay, this is system of particles, so we will study about the collection of different point objects, okay, and how their motion is affecting motion of center of mass. ठीक है. So first of all, uh, we will talk about the velocity of center of mass. Velocity of center of mass. Okay. Now, previously what we had done, that we had defined the position of center of mass. Okay, position, you can say the position of the center of mass was like, suppose uh, x is the position of center of mass, so we can write that as m1 x1 plus m2 x2 upon m1 plus m2 and so on. Okay, this is for two objects, so we can write it as summation of mx, okay, summation of mass into its x coordinate by summation of mass. Okay, this is what we were writing earlier, or if you want to write it in for a continuous objects, it becomes integration. We have seen that. Now suppose you differentiate this. Okay, what will happen if you differentiate this equation with respect to time? Okay, if we differentiate this function, if we differentiate this equation with respect to time, what should happen is that it should become dx cm by dt. Okay, x is representing, you can say, your displacement in a manner. Okay, it is representing your position vector in a manner. So if you differentiate your position, if you differentiate your distance, if you differentiate your displacement, it starts representing your velocity. Okay, it starts representing speed of cm or velocity of the center of mass. Okay, this you can write it as a vector form. So if you write it in vector, it will become velocity. If you write it as distance, it will become speed. Okay, so this becomes vcm. The LHS side of the equation becomes vcm. Okay, now let's talk about the right hand side. Let's talk about the right hand side. You are differentiating the right hand side. Okay, so we can see that the denominator is a constant. Okay, then it is divided in numerator and denominator. So denominator is a constant, so that will jump out of integration, sorry, differentiation. Okay, so it will become 1 upon m1 plus m2. Okay, it will jump out of differentiation, and now you will be left with differentiation of m1 x1 plus m2 x2 and so on. Okay, you can write it in summation also, but I am doing for 2 point objects so that we can generalize the result afterwards. Yeah. Acha. Now VCM comes out to be 1 upon m1 plus m2 into. Now if we try to differentiate this, you can see there are two terms, m1 x1, m2 x2. So we will differentiate them separately. Now if we are going to differentiate them separately, you can see that m1 x1, in that m1 is a constant. Okay, mass of the point object will be constant, and it won't be varying. So since the mass of the point object is constant, it will jump out of integration, and you have to jump out of differentiation, and you have to differentiate only x1. Okay, so differentiation of dx1 by dt, okay, that will become velocity of the first particle, that is v1. Okay, similarly For the second term also m2x2. Okay, m2 is a constant, it will jump out of differentiation. X2 will be differentiated to give velocity of the second particle. So here you can see that the velocity of center of mass has a formula of m1 v1 plus m2 v2 upon m1 plus m2. Okay, m1 v1 plus m2 v2 upon m1 plus m2. This is the formula for center of mass, velocity of center of mass. Okay, this can also be written in the form of summation m into v upon summation summation m. Okay, so this is how you can write velocity of center of mass. Okay, this is how we define velocity of center of mass. Now, if you are defining velocity, so all these terms will be velocities only. Okay, you have to be careful for that. That if you are defining the velocity of center of mass, okay, you have to keep the v1 and v2 in terms of velocity only. That is with their directions. Okay, directions also become important over here. Okay, how? Let's see. For example, okay, let's see an example that suppose I have a 5 kg 2 meters per second. I have 10 kg 4 meters per second. Not 5, skip this 10. So yeah, so there are 3-point masses, 5 kg, 10 kg, and 10 kg with different speeds, different velocities. Okay, we have to find what is the velocity of center of mass in this case. Okay, so see here, when they are talking about velocity, we don't have to worry about the position of the system. Okay, we don't have to worry
Sir,
about the. Yes.
your voice is not clear, so I can hear some disturbance suddenly.
Disturbance, yeah.
Like cracking or something like that, so vibrating, cracking sometime.
अच्छा 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 ओके ओके ठीक है now it is clear ना yes now is it clear
Yes, sir, now it's clear.
अच्छा ठीक है अच्छा
Sir, could you zoom out a bit?
yes ठीक है so when we are doing this question when we are being asked to find the velocity of center of mass ठीक है so what we can do is first of all we don't have to worry about the position of the particles ठीक है where they are kept what is the relative position what is the distance between them that is not important to us ठीक है because see when we are writing vcm ठीक है there is no use for no use for the x coordinate or the y coordinate of the particle or the distance between them ठीक है what is important we just need their individual velocities ठीक है so individual velocities of the particle is given to us है ना so we don't have to worry about it acha now if we don't have to worry about it what we can do is simply use the formula ठीक है vcm is m1 v1 plus m2 v2 plus m3 v3 upon m1 plus m2 plus m3 ठीक है so this is the formula for three particles ठीक है if it would have been four another term would be added if it would have been five another term would have been added and so on it goes on अच्छा m1 is how much let this be m1 this be m2 this be m3 this be v1 v2 and v3 ठीक है so first of all if we are talking about m1 ठीक है so m1 is 5 है ना v1 is 2 I cap ठीक है I need to keep my velocities not speeds ठीक है almost every time ठीक है almost every time you have to keep speeds only sorry velocities only ठीक है you don't need to calculate speeds ठीक है we always calculate the motion of center of particle with velocity ठीक है because direction has an important role to play Yes, something like that should be the answer. Okay, so what I am trying to say is you always need to be careful that you have what is the direction of the speed, direction of the velocity. Okay, you have to always think about that. So here, 5 into 2 I cap will be m1 v1. Okay, 5 into 2 I cap will be m1 v1 plus m2 v2 m2 v2. M2 is how much? 10. V2 is how much? 4 j cap. Okay, V2 is 4 j cap. And what about M3 V3? M3 is 10. V3 is 2 minus I cap. Okay, define this as x, this as y. So I cap j cap can be seen clearly. Okay, it can be visible. Divided by m1 plus m2 plus m3. 5 plus 10 plus 10. Okay. So from here, if you calculate it, whatever should be the answer, 10 minus 20 minus 10 I cap plus 40 j cap upon 25. So whatever simplifies, okay, it simplifies to whatever, let it be. Okay, we are not interested in the calculation part. That you can do. Okay, that is easy, that is simple. You can do that. That is basic. Okay, so this is the way to calculate velocity of the center of mass. Okay, always the directions of the particle are important. Okay, there are very few cases, very rare cases you can say where we calculate speed. Okay, we almost every time we calculate velocities only. Okay, so don't worry about it. This is the method to solve it. Yeah. Acha. So if this is velocity of center of mass, है now you can see here. You can see here. Basically, what we are calculating. Yes, yes, yes. Okay. Basically, what you can see here that we are calculating the individual momentums of each of the particle. Okay, here basically you are calculating the momentum of each of the particle. So see, if you just try to rearrange the you rearrange the formula. Okay, you can write a note. Okay, like an extra point that if if you rearrange the formula, okay, you can see that summation m into vcm, summation m into vcm is equal to summation of mv. Okay, this is the formula which we are getting for velocity of center of mass. Okay, now this summation m is basically the mass of the system. Okay, it is basically the total mass of the system. So that means it is basically the total mass of center of mass. Okay, here when I told that the total mass is coming out to be 25 centimeter, that means what? That I can replace these three masses. I can replace these three masses with a single point mass of 25 kg with the velocity of vcm, whichever direction it is coming. Okay, just for reference I am drawing this. This is the concept of center of mass, that you are replacing all the 3 point objects with a single point mass. है So that single point mass is having how much mass? The total mass, that is sigma m. Okay, so we can say that this is mcm. Okay, this is the total mass of the center of mass. Okay, net mass of the center of mass. है ना? Acha, now if it can be replaced like this, you can see that the LHS, okay, the left hand side is creating, it is representing, you can say, the momentum of center of mass. Okay, it is representing the momentum of center of mass, which is equal to the summation of individual momentum. Okay, it is basically the summation of individual momentums. Okay, this is also vector. Okay, so momentum of center of mass is nothing. It is just the summation of the individual particles. There is no division, nothing. Okay, so momentum of center of mass is summation of momentum of each particle. That's it. Okay, so whether you calculate VCM or whether you calculate momentum of the center of mass, it is one and the same. It is one and the same. Okay, so we don't have to worry about that. What should be the how to calculate this? Okay, here if I had multiplied it by 25 into VCM, this would be representing momentum of center of mass, which is equal to minus 10 I cap plus 40 J cap. That's it. This is the momentum of center of mass. खत्म. ठीक है ना? अच्छा. Now, once we have calculated this velocity and momentum, now we can move on to acceleration. ठीक है, acceleration of center of mass. Acceleration of center of mass. ठीक है. So again, simple. ठीक है, acceleration of center of mass also has a very simple formula. ठीक है, we won't waste much time on this. ठीक है, because it is a very simple concept. You can understand it easily. ठीक है, the most easy concept of this chapter is this acceleration of center of mass. ठीक है, so VCM, when I say VCM, ठीक है, VCM can be written as what? M1 V1 plus M2 V2 upon M1 plus M2. ठीक है, this is what we have written for this velocity of center of mass. This is the formula for velocity of center of mass. Yeah. So now if you want the velocity, if you want the acceleration of center of mass, okay, what we can do is we can simply differentiate the result. Okay, we can simply differentiate it once again with respect to time. Same as we did with distance, same as we did with position. So if you differentiate velocity, okay, it will become on the LHS, it will become acceleration of center of mass. Okay, on the LHS, it will become acceleration of center of mass. And by the same logic, okay, as we differentiated displacement, okay, with the same logic, we can do here that it will be M1A1 plus M2A2 upon M1 plus M2. Okay, so this will be the acceleration of center of mass. Okay, simple. It is the same thing. Okay, you don't have to worry about
Could
it.
you
It
please
is,
scroll up?
yes, yes. Okay, it is the same thing. Okay, just instead of velocity, we are using acceleration. Okay, instead of displacement, we are using velocities. The formula itself is same. Okay, there is no as such change in the formula. Okay, hope it is clear. Yeah. Simple thing. Okay, I am not even going to do a question on this because see, the question will be in the same manner as velocity only. Okay, there is no difference. There is no difference between velocity and acceleration formulas. Okay, everything is same. Okay, अच्छा. Write this. ठीक है. Yes, you have written yes. ठीक है. So this was acceleration of center of mass. Now see, the formula itself is not important for us. ठीक है. What it represents is important for us. ठीक है. That means what I'm trying to say that suppose I want to write the net force on the system. ठीक है. Suppose I want to write the net force on a system of particles. ठीक है. Suppose there are F1, F2, F3 and so on forces acting on M1, M2, M3 and so on. ठीक है. And I want to calculate the net force on the particle and sorry, net force on the system. ठीक है. So what I can do is instead of individually calculating each of the force, ठीक है, F1 plus F2 plus F3 and so on, ठीक है, vectors, these are all vectors. Instead of adding all of these vectors individually, what I will do is I will simply calculate the center of mass acceleration. ठीक है, acceleration of the center of mass. है ना? What I will do is I will remove all the particles. ठीक है, take my center of mass. ठीक है, concentrate all the masses at that point and write that acceleration above it. Okay, that acceleration of center of mass will be there above the center of mass. Then the force about that system, okay, about that center of mass, can be written as MACM. Okay, what is M? M is the total mass of system, that is summation M. Okay, that is summation M, what I just told you in case of momentum, mass of center of mass. Okay, summation of all the masses. And ACM, we have just seen the formula. Okay, so F net of the system, F net of the system can be written as MACM. Okay, acha. Now force, okay, if you talk about force, है ना, net force of the system. Okay, you can talk force on center of mass. You can write the heading here as force on center of mass. Okay, if you want, you can write it. Okay, it doesn't matter. It is not a very special topic. Okay, it is a very simple, basic topic. Acha. Now, where were we? If F net on the system, okay, F net can be defined. Net force can be defined as dp by dt. Okay, dp by dt. Yeah. And just now, okay, this is you can say another type of derivation, okay, for getting this result. And this is another derivation for getting the same result, that is F is equals to MACM. Okay, just somebody's mic is on, I guess. Yeah. So mute it, no problem. Okay. So F net is equals to dp by dt. What is this P? P is the momentum of center of mass. Okay, P is the momentum of center of mass here. So if P is the momentum of center of mass, you can write this P as d by dt of M. M can be written, in fact, capital M into VCM. Okay, total mass of the system into velocity of the center of mass. Okay, total mass of the system into velocity of center of mass. So this capital M, net mass, will jump out. So it will become M by d by dt of VCM. So from here also you can write that it is MACM. F net of the system can be written as MACM. Okay. Now this is just a small, kind of derivation kind of thing. Okay, not very much important for us. What is important for us is the conservation of momentum concept. Okay, the thing important for us is the conservation of momentum. ठीक है, conservation of momentum, है ना. So conservation of momentum is still the same. ठीक है, it is still the same. ठीक है, the logics are all the same. Just instead of saying the net force about a single mass, ठीक है, we will start saying about the center of mass. ठीक है, it is like कि the momentum of m1 and m2 is conserved. ठीक है, now we will start saying the momentum about the center of mass of m1 and m2 is conserved. That's it. That is the difference, nothing else. Everything is the same still. Like how? Like if the F net is 0. Okay, this is the criteria for conservation of momentum, that your net external force should be 0. Okay, the net external force should be 0. So F net is 0. Then I can say that your ACM, your acceleration of center of mass, is 0. If this is happening, then I can say that P of center of mass is constant. Or let's not write it like this. Let's write that dpcm by dt is 0. Okay, so differentiation of anything will be 0 if that anything is a constant. Okay, if it is a constant, its differentiation will be 0. So pcm must be constant. PCM must be constant. Hence, I can say that initial momentum of center of mass will be equal to final momentum of center of mass if your net force is coming out to be 0. Okay, this is how you can see in case of center of mass. Okay, same thing, not much of a difference, but one thing you have to remember, that acceleration, you can write it as a note, that acceleration of center of mass is what? It is 0. What does this represent? What does this show? Okay, what it is representing, that acceleration of center of mass is 0. It means that it can mean two things. Okay, it has two possibilities. One possibility is that
Yes,
the
you have.
velocity, uh, ठीक है, anybody, what does this mean? ठीक है, you only tell about velocity. If acceleration of center of mass is 0, there are two possibilities of velocities of center of mass. And what is that result, you can say, conclusion? Okay, by the time you write, one result is very good, that VCM is 0. No doubt in that. VCM is 0. Yes. What is the other conclusion? What is the second conclusion?
Constant velocity.
That's it. Very important thing. The velocity is either
Certain.
zero. Okay, no problem. Yeah. And also this is very important thing. You have to always remember the basics. है ना? Yes.
सर
Initial and
scroll
final
up.
velocity. अच्छा. You are writing. ठीक है, right. No problem. That's it. Velocity. I get it. You all are you all know. Okay. So if acceleration of center of mass is 0, there are two possibilities. One possibility is that your center of mass has 0 velocity, okay, that it is at rest. And the second conclusion is that the velocity of center of mass is constant. That means it is showing constant velocity motion. It is moving equal distances in equal time intervals. Okay, so there are two possibilities which can occur here. So that is one, VCM is 0, and the other is VCM is constant. VCM is constant. So these are the two possibilities. Acha. We are not as much interested in constant velocity as much as we are interested in zero, rest. Center of mass is at rest. Why? Because it creates some unique situations. Okay, it creates some unique problems which are very interesting to solve if you know the basic. Okay. So let's see that. Okay, I hope everybody has written this. है ना? Or do you want time, more time? Okay. So I guess everybody has written this. Hmm. Now see, if velocity of center of mass is 0, what can you comment? What can you comment about xcm? What can you comment about xcm? No, there are not two possibilities. There is only one possibility. What can we comment about the distance, or you can say the displacement? Let's write it as distance x. Let's write it as displacement of center of mass. Okay, what can you comment about the displacement of center of mass?
0.
0. That's it. The displacement of center of mass is 0. Simple. If your velocity is 0, your displacement will also be 0. Okay, velocity 0 means what? The particle is not moving anywhere. If the particle is not moving anywhere, obviously the displacement will be 0. It will be remaining at that point only. Okay. So if displacement is 0, what I can conclude is that the initial position of center of mass will be equal to the final position of center of mass. So center of mass is not moving anywhere, hence center of mass is at rest. This is a very unique situation. A center of mass equal to 0 means your net external force on the system is 0. When the net external force on the system is 0, there is a possibility, there is a 50% chance that your center of mass is at rest and its position is not changing. Okay. So this creates some unique situations, like let's see a question. Okay. This is a very common question. This is a man planck problem. It is called as man planck problem. Okay. You must have heard about it. That suppose I have a plank. ठीक है, on smooth surface, ठीक है, there is no friction, it is absolutely smooth, frictionless surface, है ना, and a man is standing on one of the ends of the plank, ठीक है, AB, he is standing on the end B. Suppose the mass of the plank is capital M and mass of the man is small m, ठीक है. Now what happens is that the man, ठीक है, this was the initial position, this is initial condition, everything is at rest, ठीक है, no one is moving anywhere, ठीक है. Now what happens, let's not draw it like now. Eh, now what happens is it will be given in statement form that there is a man of mass small m and a plank of mass capital M on which the man is standing at one of the ends of the plank, ठीक है. Then what they will say is that the man suddenly starts to move towards the other end of the plank, ठीक है, he suddenly starts to move to the other end of the plank, and when he reaches the other end of the plank, you have to tell by how much has the plank moved, okay. I guess you are able to imagine that if the man starts moving towards this side, okay, towards the A end, है ना, you can imagine that the plank will start moving in the backward direction. How, ठीक है, you can see examples, like suppose you are standing in a boat, ठीक है, you are standing in a boat and you jump out of the boat, ठीक है, suppose you jump out of the boat, so what happens is that when you jump out, the boat starts to move in the opposite direction, ठीक है, boat starts to move in the backward direction, है ना. So same thing happens with the plank, ठीक है, there is no friction over here, there is no resistance of motion over here. So if the man moves towards A, the plank, ठीक है, will behave like boat and will start moving in the opposite direction, it will start moving in the opposite direction, ठीक है. Now 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 what they ask is that by what distance, ठीक है, question will be asked that, let me write the statement, by what distance does the plank move when man, okay, relatively the man reached point A, okay, he was moving on the plank, so relatively he reached point A. So you can see that when he reached point A, the plank has moved by some distance x, ठीक है, you can see that the end of the plank, ठीक है, A end of the plank has moved by some distance x, ठीक है. You have to basically determine what is the value of this x, by how much has this plank moved, ठीक है. So how to do that, it is very simple, ठीक है, it is the concept which I have just discussed, that is the note point, that, see, let's start from starting only, ठीक है, this is the answer part,
So
that
please
was
roll
question,
up a bit.
okay, write the question first, no problem. Okay.
Yes, sir.
Okay, so how to solve this kind of question, that by how much the plank will be shifted, okay, this is a very important question, okay, almost every time we expect such a question to be asked, okay, regarding center of mass and relative motion and all, okay. So let's draw coordinate axis first, okay, this is my coordinate axis x and y, ठीक है. Initially the plank was like this, ठीक है, A B. Initially one end of the plank was at origin and the man was standing at point B, ठीक है, his mass was small m, the capital S is friction, huh? Now after he moved, ठीक है, what happened is, let me draw this like this only, ठीक है, we are drawing it on this one only, make it easier, ठीक है. Once the man reached end A, what happened is that the plank also moved by distance x, ठीक है, plank moved in the opposite direction by distance x when the man reached point A. Okay, so we have to find this x only. Now see, just tell me, is there any net external force on the system initially? Okay, this is the initial condition. This is the initial condition. This is the final condition. Is there any net force on the system initially? Yes. Anybody? No, no idea. Okay. See here, the net force on the system is initially zero. Why? Why? You must be thinking, sir, that if the man is moving, there must be some friction on it. Okay, there must be some friction. That is why he is moving. Okay. Now see, I am talking about the system. I am not talking about individual man or the individual plank. I am talking about the man plus plank system, complete system. Okay, so on that complete system, if you see, this is my complete system, है ना? Is there any externally applied force like this, or like this in any manner? No, it is not there. Hence, so what we can say is that whatever force the man is creating is internal force. Okay, the man the man who is applying force on the plank, or the plank which is applying force on the man, are all internal forces. They are all friction. Friction is all internal forces in this situation. Okay, if I would have been studying, okay, if I would have been studying only the man, okay, suppose I am drawing the free body diagram of only the man, then definitely I would have written friction force like this. Okay, no doubt in that. है ना? But 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 I am studying the plank as well. I am studying the plank as well at the same time. So on the plank there is a friction force like this also. So the net force on this will what? This will cancel out. So net force on this will become zero. Okay, when you are combining these two, obviously the frictional force will cancel out. Okay, so that is why the net force on the system here. Okay, this is just explanation. No need to write this. Okay, hence I can say that the net force on the system initially is zero. In fact, when it is moving, okay, when the man is moving, when the plank is moving backward, still the net force on the system is zero. Still the net force on the system will be zero, because still only friction is there. Only friction is there. No one is pushing the plank, or no one is pushing the man externally from outside. है ना? So net force is zero. Even in the final case, the net force on the system is zero. Net force on the system is zero. If the net force on the system is zero, then acceleration of center of mass will be zero. Then that will create two possibilities. Either the position of center of mass is at rest, okay, it is not moving, or the velocity of center of mass is constant. Okay. Now here if you see, you can say that initially the center of mass was at rest. Okay, because the man was also at rest, the plank was also at rest. So the net center of mass, if you calculate m1v1 plus m2v2, so that will be m into 0 plus m into 0, that is 0 plus 0, it will be 0. Okay, so center of mass, initial center of mass of initial velocity of center of mass, that will come out to be 0. If that is 0, I can say that the position of center of mass initially and position of center of mass finally, they should be equal. They should be equal. So only one thing remains for us to do is to calculate the xcm initial, xcm final. That's it. Then equate them. That's it. If you equate them, you have the answer. ठीक है. So let's see, let's start, है ना. Now the center of mass of this man will be on himself only. ठीक है, his center of mass will be on him only. ठीक है, somewhere on near his center. ठीक है, so center of mass approximately we can write that this length is L. So coordinates of the center of mass of man can be written as L comma 0. ठीक है, L comma 0, we are not taking the height, we are not taking anything in y direction, assuming it to be on the x axis only. ठीक है. अच्छा, the center of mass of the plank. ठीक है, the center of mass of the plank, you can write this as cm1. ठीक है, and this man as cm2. ठीक है, so cm1 coordinates of this will be how much? It will be at a distance l by 2. So this is l by 2 comma 0. है ना. So now if you write xcm initial, if you write xcm initial, it will be m1 x1. M1 is how much? M1 is capital M. X1 is how much? L by 2 plus M2 x2. M2 is how much? Small m. X2 is how much? L upon M plus M. This is the initial center of mass. ठीक है, this is the initial center of mass, है ना.
Excuse me, sir.
Yes.
So I got disconnected. Can you explain how you got L by 2 and L?
अच्छा, ठीक है. Now see, the L by 2, see L by 2 is basic. ठीक है, the center of mass of the rod is at a distance of L by 2 from one of the end. That is just in the last class we had written that table. ठीक है, that list, complete list of center of masses. So in that I have written that the center of mass of a uniform rod, ठीक है, it is at a distance of L by 2 from one of the ends. It is at the midpoint of the rod. So same thing. ठीक है, it is kind of like a rod. ठीक है, so hence the center of mass is at a distance of L by 2 on the x-axis, है ना. So center of mass for 1 comes out to be L by 2 comma 0. Now what about the second mass? ठीक है, that is the man. ठीक है, the man center of mass will be in on itself only. ठीक है, his center of mass will be his center of body. ठीक है, center of body will be somewhere here. I am not interested in what is the exact location, but still it will be somewhere on the body. Acha, that man is standing at one end of the plank, and in the question already it is given that the length of the plank is L. ठीक है, so from the origin the man is standing at a distance L. ठीक है, so its x coordinate will be how much? Its x coordinate will be L, and its x coordinate will be L. So the coordinates of center of mass for man will become L comma 0. ठीक है, so that is why now I can write m1 x1 plus m2 x2 upon m1 plus m2. That is this. ठीक है, so this is x in x coordinate of center of mass initially. ठीक है, let's keep it, no problem, let's keep it, and just keep it in mind. अच्छा, now let's calculate center of mass final. ठीक है, xcm final. So again see, this is still the origin, this is still the origin. ठीक है, but now the small m mass is at a distance of x from the origin. ठीक है, small m mass is at a distance of x from the origin. So what I can write, the coordinates of small m mass as x comma 0. ठीक है, earlier it was L comma 0, now it is x comma 0. ठीक है, the center of mass of the plank, center of mass of the plank will still be at the midpoint of the rod, will be still at the midpoint of the plank. So this length is how much? This length is L by 2. ठीक है, let's write this as cm2 only. ठीक है, this is cm1, है ना. Now the coordinates of the center of mass of first one, that is of the plank, ठीक है, that can be written as how much? What is the x coordinate? You can see from the origin the center of mass is at a distance of L by 2 plus x comma 0. ठीक है, the coordinates of center of mass from the origin is L by 2 plus x comma 0. Yes, this should be the answer. ठीक है, so if you calculate the final xcm, ठीक है, xcm final if you calculate, ठीक है, you can see what it will come out, m1 x1. So m1 is how much? Capital M, we are talking about the plank as m1, and x1 now in the final case has become L by 2 plus x. L by 2 plus x, ठीक है, plus the m1 m2 x2, sorry, m2 is small m, and x2 is how much? It is x. M2 is sorry, x2 is x, divided by m plus m, divided by m plus m, ठीक है. So now see, what we want is to equate these two, ठीक है. Finally what we will do is we will equate the two values, xcm initial is equal to xcm final, because we know that the velocity of center of mass is 0, so their initial position should be equal. Sorry, their position of center of mass should not move, ठीक है, because the vcm came out to be 0, है ना. So if you equate it, you can see that, ठीक है, this is initial and this is final. So this denominator gets cancelled, ठीक है. In fact, this, why will I remove you from the meeting here? And how can I remove you from the meeting? I'm
Sir,
teaching
some
here.
other student must have done that.
How? I am only the one. Eh?
So we are attendees.
How is that possible?
He's saying that physics to removed you.
I don't know how is that happening, but I did all of that thing here also. That who can present thing I now. Please don't do this, है ना? ठीक है. चलो. Don't do such things, है ना? They're just wasting time, है ना? Don't waste time. You don't have much time also, है ना? चलो. So we were on the calculation, so we can write ml by 2 plus small ml is equals to ml by 2 plus mx plus small mx, ठीक है. So capital ml by 2, capital ml by 2 get cancelled. So from here you can see that the value of x, ठीक है, value of x is coming out to be small ml upon capital M plus small m, ठीक है. X is coming out to be small ml upon capital M plus small m, ठीक है. How to remember this formula? First of all, what is x? X is the displacement of Planck, ठीक है. X is the displacement of Planck. This is equal to, ठीक है, because you see here when I drew the value of x, I am representing only the Planck, ठीक है, the displacement of Planck with respect to the ground. So x calculated is xp, ठीक है. X is representing the displacement of Planck, which is equal to the mass of man, ठीक है, the mass of man into the relative length L relative, ठीक है. What is L relative? L relative is the relative length which the man has moved on the plank, ठीक है. Because you can see here the man moved relative to the plank a distance of length L, ठीक है. Man moved a distance capital L on the plank, not on the ground. On the ground, see, with respect to ground, let's talk with respect to ground. With respect to ground, he moved only this much, ठीक है. This is not L, ठीक है. This length is not L, है ना. But as per, if you ask the man how much did he move, he will say that I moved the whole length of the plank, ठीक है. So relative to him, you can say, relative to the man, the distance he covered on the plank was L. So that is why I have written that as L relative, ठीक है. This is how you remember this formula. This is how you understand this formula, ठीक है. Divided by the mass man, okay, let's write it as small m only, mass of man plus the mass of Planck. This is how you remember this formula. Okay. Now suppose in some case, okay, in some question, they ask you that what is the displacement of Planck if the man moves just a distance of L by 2. Okay, he moves till only the midpoint of the Planck. Then what is the displacement? Okay, so simple. Everything else you know. Okay, this and this you know. Just instead of L relative, okay, you will replace L by 2. Okay, when the man was moving the complete distance of the length, I replaced L. Okay, I replaced that. But now since he is moving only point of the Planck, okay, since he is moving only till the midpoint of the Planck, I will replace that as L by 2, and you will have the answer. That's it, finished. Okay, is it clear? Is it understood? And now, so this is how you can remember the formula. Okay, if you want, you can write it now. Okay. Acha. Uh, we calculated the displacement of the distance covered, okay, by the Planck. Okay, we could have also calculated the distance covered by man with respect to the ground. Okay, we could also have calculated this distance. How? You can see that once you have the value of xp, xpc, this total length is how much? This total length is L. Okay, from the upper diagram you can see that the total length is L. And he moved the distance x man like this. So x man can be written as L minus xp. Simple. Okay, once you have the value of xp, just subtract it from the total length of the Planck. Okay, if you subtract it from the total length of the Planck, this will be the distance covered by the man with ground, not with respect to himself. Okay, for an observer on the ground, he moved only this much, and he moved only this much. Okay, so that is not formula. It is not a new formula. Okay, only what happens is, okay, you can also see the difference here. Achha, you were out now. See, I am not saying that the Planck is not displaced. I am saying that the center of mass is not moving anywhere. Okay, that means don't do this. This has become a very complicated diagram. Okay, just see for explanation purpose only. Don't draw this diagram. Okay, initially the Planck and the man were like this. Okay, so the center of mass was somewhere over here. This is the center of mass one. So center of mass of the system was somewhere over here. Okay, center over here. Now what happened? That small m mass and capital M mass interchanged position. You can say in a term, you can say that they interchanged the position. Okay. So still, if the center of mass has to stay here, if the center of mass has to stay here, and small m mass is over here, then the capital M mass must move over here. It should move over there on the other side. Okay, then only it is possible that the center of mass will remain over here. Otherwise, if I move the center of mass on this side only, okay, suppose if the center of mass of the Planck was on this side of the center of mass only, okay, just a minute, just a minute. If the center of mass of the Planck was on this side, then the center of mass would have been somewhere between these two, na? So the center of mass would have moved. It would have moved, and that is not possible. Okay, by the logic of force, that is not possible. So therefore, what needs to be done is, what should have happened, what will be happening is that the Planck will be moving its center of mass from here to here, so that the center of mass of the system remains at that exact position. Okay, it does not move anywhere. Okay, so just to make the position of center of mass of the system stable, okay, the Plancks move towards the right and the man moves towards the left. ठीक है हाँ so this is just a logic. ठीक है this is just the logic है ना. If you're not getting it, doesn't matter, you need to know the method. No one is going to ask you the logic anyway. ठीक है because in NEET and all, ठीक है application is important. ठीक है the theory is not as such important. ठीक है somewhat it is important but not very much. ठीक है so application is much more important than that. ठीक है now see once I have written the distance covered by the plank. ठीक है I told you I can also calculate the distance covered by the man with respect to the ground. ठीक है with an observer from the ground I can calculate the displacement of the man, distance covered by the man also. ठीक है that is basically what L minus XP. ठीक है so if you replace this value over here you will get the formula as capital M into L upon M plus M. Simple. ठीक है again the simple thing only. ठीक है what has happened, instead of the mass of man in the numerator it has come mass of plank in the numerator, L relative. ठीक है distance covered, relative distance moved upon mass of man plus mass of plank. ठीक है everything else is same, just the this value. ठीक है the mass in the numerator has changed. If you are talking about plank, in the numerator the mass is man. ठीक है if you are talking about the man, in the numerator the mass is of plank. ठीक है so this is a very easy formula to remember. Once you remember it, ठीक है once you have it in your mind, ठीक है it becomes very easy to manipulate it, you can say. ठीक है to modify it. ठीक है yeah. So if you want you can remember both the formulas, but I prefer to remember only the first formula, that is the distance moved by the plank. Okay, because of the man you can calculate it easily just by manipulating the terms. Yeah. Acha. Now see, this was all about displacement and all. Okay, this is not important, don't remember, don't write it. This was all about distance. What about velocity? Okay, what about velocity? Suppose it is said that the man moves with velocity of v with respect to plank. ठीक है then find velocity of plank with respect to ground. Find the velocity of man with a velocity of plank with respect to ground. Suppose this is the question. Suppose this is the value which you have to calculate. Suppose velocity is given instead of displacement now. ठीक है so nothing, same. ठीक है the formula of xp is still this only. xp is what? Mass of man. ठीक है small m is man. ठीक है I'm not going to write m man and m plank every time. ठीक है understand this, that small m is the mass of man, capital M is the mass of plank in normal terms. ठीक है into L relative. ठीक है distance displacement relative divided by mass of plank plus mass of man. ठीक है to get velocity of the plank. ठीक है what I have to do is differentiate it. ठीक है what I have to do is differentiate it. Simple. So velocity of plank will become what? Velocity of plank will be equal to mass of man will remain the same. The distance moved relative will now become v relative, velocity relative upon m plus m. That's it. This is the formula for velocity of plank with respect to ground. ठीक है you can write it as velocity of plank with respect to ground. Simple. ठीक है you just have to differentiate the terms. Even if acceleration was asked, again you would have differentiated it again. ठीक है but acceleration is not asked. ठीक है till now never it has been asked. ठीक है just for being on the safe side I am telling you that. ठीक है. So this is how you can see the velocity. ठीक है, this is how you can see the velocity of the plank. हाँ, ठीक है ना. So I guess you are getting the idea of how to see the motion of center of mass. ठीक है, if the net force on the center of mass is 0, ठीक है, its motion will be, its position will, position can either be constant. ठीक है, its sorry, velocity can either be constant or its position can be constant. ठीक है, its position will be same. ठीक है, so variations can be created. ठीक है, this is standard question, that is why I have done this question. ठीक है, variations can be created, so be ready for variations also. ठीक है, there are possibilities, there are different possibilities that could happen. ठीक है, अच्छा. Now अच्छा, another thing you can note down. ठीक है, another point you can write is that suppose I have a projectile. ठीक है, suppose I have a projectile. ठीक है, I have thrown a grenade at an angle theta from this point with an initial velocity u. ठीक है, now what happens is it should have traveled this path. It should have traveled this path. ठीक है, but what happens is when it reaches the topmost point, it explodes. ठीक है, it explodes and breaks into two parts. It explodes and breaks into two parts. One part goes like this. ठीक है, other part goes like this, somewhere like this. ठीक है, it can go in any random manner, है ना. So I can say that one part jumps over here. ठीक है, this is m1. ठीक है, and the other part comes over here, m2. ठीक है, now what will be their, question can be asked that what will be their relative distances. ठीक है, what is the value of x2 and what is the value of x1, what is the relative positions. ठीक है, so that is again easy to calculate. How? See, when you threw the grenade, ठीक है, the center of mass was moving along this path only. The center of mass was moving along the path of the projectile only, original projectile. ठीक है, now when it exploded, it exploded because of internal forces. ठीक है, there was no external force involved in it, है ना. You did not apply a external compression force so that the grenade exploded. No. ठीक है, it exploded on its own because of internal chemical reaction. It exploded, है ना. So since it is exploding because of its internal reactions, internal forces, external force explosion was not there. ठीक है, so since there was no external force causing that explosion, the center of mass remained on the same path. The center of mass remained on the same path. The individual particles, ठीक है, m1 and m2 were on different paths. ठीक है, they were on different path, but their relative center of mass was on this path. ठीक है, when it came over here like this, its center of mass is still here. ठीक है, this is the path of center of mass. This is center of mass, center of mass, center of mass, center of mass. ठीक है, so even after explosion, ठीक है, even after the explosion, the center of mass still remained, it still remained on the original path of the projectile. The center of mass was not deviated anywhere, it did not move anywhere, it moved on the original path of the projectile. ठीक है, now basically you know the coordinate of center of mass, you know the value of xcm. Xcm is how much? It is the range of the projectile. ठीक है, you have the value of u, you have the value of theta, you can find the value of range. So you have the x coordinate of center of mass is how much? It is range, it is the range. And x coordinate of center of mass can be written as m1 x1 plus m2 x2 upon m1 plus m2. So from here you can calculate the values of x1 and x2. One of the values will be given. Okay, like they will say that the second particle, the m2 particle falls back to the same point. Okay, fall back to the initial point of projection. So x2 will become 0. Okay, sometimes they will say that the second particle just falls vertically downwards. That means x2 will become r by 2, sorry, it will become r by 2, and so on. That one of the values will keep on varying, and you can calculate the value of x1 using this relation. Okay, is it clear? And this is a variation which can be produced, so you can solve it using this formula, and you can simply solve it using this formula. Okay, any doubts, anybody? Huh, no problem. Okay, see, what I'm saying is that let's see from the starting that suppose I have a projectile motion. Okay, a particle was projected with a speed u at an angle theta. Okay, so it was moving, and when it reached the topmost point, okay, what happened is it broke into two parts. Okay, one of the part moved like this. Okay, it moved further away. Okay, from where it should have reached. Suppose this is m1, it moved further away, and the other part fell vertically downward or in a different direction. It went somewhere. Okay, you don't have to worry about where it moved and how it moved. They will give you in the question. Okay, now what they are saying that find the position of x1. Okay, find the position of mass m1, that is x1. Find the value of x1 if if the second particle falls vertically downwards like this. This is the question. Okay, now how to find that simply you can see here that x2 is basically r by 2. Okay, this is the example. Okay, don't take it as generalized method. Okay, don't take it as a generalized formula. It is just an example that the particle is falling vertically downward. Okay, it is possible that it could have returned back to this position, or it could be somewhere between r by 2. Okay, it can be anywhere. You in the question. है ना? Acha. Now if you want to find the value of m1, ठीक है, sorry, if you want to find the value of x1, okay, what you can do is you can use this formula. R is equals to m1 x1 plus m2 x2 upon m1 plus m2. Why I am saying this? Because the distance of center of mass is r. Okay, when both the masses reach the bottom, okay, when they touch the ground, the center of mass is basically at this position only. Okay, the center of mass has not moved. It has not deviated from the original path of the projectile. The center of mass initially was over here, then it moved over here, then it moved over here. Then when it was exploding, still the center of mass was on the path only. Okay, when it exploded, there two particles was generated. Okay, they moved off in different directions, but still the center of mass remained on this original path of the projectile only. It did not deviate. Okay, why it did not deviate? Because the explosion was caused by internal forces only. It is something like friction. Okay, in the previous question there was friction. In this case it is chemical reaction, chemical explosion. Okay, that is internal only. Okay, it is not something that creates external forces is creating explosion. It is not like that. Okay, so since the internal forces are only creating it, the motion of center of mass is unaffected. Motion of the center of mass is unaffected. Center of mass keeps on moving along the same projectile path. Okay, same parabolic path. M1 and M2 fly off in different direction. That is possible. Okay, it is like ki M1 and M2 are creating the center of mass, so they can do anything, but the center of mass can do nothing. Okay, so finally when the center of mass is over here, its distance is how much? Its distance is capital R, and its distance is capital R. So I can apply the formula of center of mass and get the value of x1 and x2, whichever value they are asking. Okay, So this is the kind of question they can ask. Okay, this is one variation. Okay, so your motion of center of mass is also done. Okay, now let's move on to uh, moment of inertia. Okay, this is almost everything about your system of particles. Okay, more variations are possible. Okay, variations can be created. Okay, so for that you have to do practice. Okay, basic is done. Okay, all the basics which can be taught to you is done. Okay, variations, for variation you need practice. You do practice, you have your modules and all. Okay, do your practice, ask doubts, clear your doubts, clear about variations. Okay, that is the only method. Okay, there is no other way to learn physics. Okay, I cannot teach everything in the class. Okay, even if I teach, you won't get everything from the class. So that is not possible also. But still, okay, I tried to complete almost everything. Okay, don't worry about that. Acha. What was I saying? Moment of inertia. Okay, let's move on to moment of inertia. Okay, so this was everything about system of particles. Okay, now we are going slowly into the rotational motion. Okay, we are going slowly into the rotational motion. So for in rotational motion, the first thing you should know, you can say it is the prerequisite. Okay, the knowledge which you require beforehand. Okay, that knowledge is moment of inertia. Okay, to understand rotational motion. Okay, rotational motion or the circular motion of big objects like circular motion of a cylinder, circular motion of a sphere. Okay, so if you want to study the circular motion of such objects, okay, we have to first of all learn some basic terms which will be going to be used in that motion. Okay, so first thing which you need to learn is your moment of inertia. Next you can write it, moment of inertia. Next heading you can write it as moment of inertia. I. Okay, it is denoted by capital I. Okay, moment of inertia. Acha, now what is moment of inertia? If you write the definition of moment of inertia, okay, it is written as the rotational analog, rotational analog of mass. Okay, moment of inertia is the rotational analog of mass. That means what? That means what? That you must have done, circular motion, basics of circular motion, that kinematics of circular motion. Okay, that you can replace linear distance, linear displacement with angular displacement. Hai na? You can replace s with theta. You can replace velocity with omega. You can replace acceleration with alpha, and that all. Okay, so what you are doing there, you are creating analogy. Okay, if you are creating that analogy, in the same manner, the mass must also have some analogy. Okay, in linear motion, in straight line motion, in rectilinear motion, okay, can be converted to angular, moment of inertia in angular momentum. Okay, it is the rotational analog of mass. Okay, so in linear motion, what is represented by mass? Okay, the mass, the work which mass does, that is creates inertia. Okay, it creates inertia. If an object has mass, it has inertia. Simple. है ना? So in angular motion, in rotational motion, it is created by moment of inertia. The moment of inertia is creating the rotational inertia which is required for rotational motion. Is it understood? And it is. If you are not getting it, just remember, whenever you see mass, in linear formulas, and you want to write it in rotational motion, just replace mass with I. That's it. Moment of inertia. Like for example, suppose I want to write kinetic energy. Kinetic energy in linear motion. In linear is written as half mv square. In linear it is written as half mv square. But in angular, when you write kinetic energy, it will be written as half I. ओमेगा स्क्वायर, ठीक है. वेलोसिटी इज रिप्लेस्ड बाय ओमेगा, दैट इज नो डाउट, ठीक है. यू मस्ट हैव डन दिस, ठीक है. वेलोसिटी इज रिप्लेस्ड बाय ओमेगा, दैट इज सिंपल, दैट इज यू हैव डन. बट the mass is also replaced by moment of inertia. Okay, so wherever you get mass you can replace it by inertia. Like suppose force is there, force is written as mass into acceleration. Okay, not, let's not write force now. Okay, we will learn about that. Okay, let's talk about momentum. Linear momentum is written as mass into velocity. Yes, linear momentum is mass into velocity. So angular momentum, that is represented by L. Okay, angular momentum is written as mass is replaced by I, it is represented as I, into velocity is replaced as omega. L is equals to I omega. This is the formula. This is correct formula. This is completely correct formula. Okay, this is not some jugad or anything. Okay, it is a trick to remember these formulas. Okay, you remember the linear formulas, you remember the angular formulas. Okay, now this was the basic. Okay, but how to calculate angular momentum? Sorry, moment of inertia. Okay, angular momentum, that we will see later on. But how to calculate moment of inertia? Okay, so that is also simple. The moment of inertia has a very basic simple formula, that is mr square. mr square. That means, suppose, for example, okay, this is the formula, you have to remember this. Okay, this is for point objects. This also you have to remember, that I is equals to mr square only and only for point objects. Okay, like for example, suppose there is a mass m. Okay, and this is rotating about a axis like this. Yes. Okay, so just see in the example. Okay, that I am talking about a point mass small m. Okay, that small m is rotating about the axis. You can see that this a dash. Okay, this a dash is the axis. This c is the center, and about this axis only it is rotating. If you rotate a dash about it, if you revolve a dash, okay, the mass will start moving itself. Okay, so the if the mass is moving about a fixed axis at a particular distance, then the moment of inertia of this mass, will be m r square. Okay, it will be m r square. Okay, this is very important. In most of the cases, most of the students forget to write r square, they write it as mr only. Okay, so that creates problem. Okay, don't do such things. है ना? So I is equals to mr square. This is moment of inertia. This is how you define moment of inertia for point objects. Now what about combination of point objects? Okay, what about the combination of point objects? Means if there are more than one point object, okay, rotating about a fixed axis. So let's see for that also. Okay, let's draw the axis only. Okay, now see, to a fixed axis, to a fixed line a dash. Okay, I have connected I have connected four different masses at different lengths, r1, r2, r3 and r4. I have connected four different masses, m1, m2, m3 and m4. Now if you rotate them about this fixed axis only, okay, always remember that your axis should be common. Different axis, suppose m1 is here, m2 is here. Okay, this is a dash, this is b dash. So we cannot, there is a different method for this calculation. Okay, you have to wait for that. Okay, now for now you cannot calculate this. Okay, the axis should be same. ठीक है, you cannot change the axis should be same. ठीक है, so if the axis is same, like in this case, a dash is the axis for m1 also, m2 also, m3 also, m4 also. Now if you want to write the moment of inertia in this case, okay, this will be rotating like this will be going around like this will be going around like this will be going around like this, okay, they will have different motions, है ना? So now if you calculate the moment of inertia, okay, it will come out to be m1 r1 square, that is the moment of inertia of 1, plus m2 r2 square, plus m3 r3 square, plus m4 r4 square. That's it. Okay, why I am directly adding them up? Because it is a very important term, okay, very important point, you can say that moment of inertia is a scalar quantity, is a scalar quantity. ठीक है, many of you confuse कि sir it is coming at as m r square, so distance is there, displacement is there, r vector can be written. ठीक है, then why it is a scalar quantity? Because understand this, it is representing mass. ठीक है, in linear motion just tell me, was mass a vector quantity? No. ठीक है, in linear also mass was scalar quantity, so in angular also the moment of inertia is a scalar quantity. ठीक है, so why create confusion over there? Simple, and it is similar to mass but in rotational motion. You can say it is mass in rotational motion like this. ठीक है, moment of inertia is mass in rotational motion, so moment of inertia is a scalar quantity. ठीक है, so that is why I calculated individual moment of inertia and directly added them. ठीक है, there is no vector sign, there is no nothing, direct add them, whatever values you are getting just add them. ठीक है, so this way you can calculate the moment of inertia of different point objects. ठीक है, अच्छा, now what about continuous objects? ठीक है, moment of inertia for continuous objects. Continuous objects. ठीक है, moment of inertia for continuous objects means what? Like again, suppose there is a rod, suppose there is a sphere, suppose there is a disk. Then what about the moment of inertia of those objects? ठीक है, so to calculate moment of inertia of those objects, first of all let's see about point object. ठीक है, moment of inertia for point objects can be written as summation of m r square. ठीक है, this is what I did over here in this formula where I was writing the moment of inertia of due to different point objects. I wrote it as summation of m r square only. ठीक है, m1 r1 square plus m2 r2 square and so on. So it is summation m r square. ठीक है, but when I go on to write m as dm, ठीक है, when I suppose I want to write the moment of inertia for a rod, ठीक है, about this axis, suppose this is the axis a dash. ठीक है, about this axis a rod is rotating, about one end the rod is being rotated like this. ठीक है, it is going in circles like this है ना, the complete circular path is being made by the rod. ठीक है, what you can do is you can take a small dm mass, ठीक है, like we did in center of mass. ठीक है, we take a very small dm mass over here. ठीक है, what will be the distance of this dm mass? Let that be r. ठीक है, the distance of this dm mass from the axis is r, so the moment of inertia of this small mass, of this very small mass will be how much? It will be r square dm. It will be r square dm, है कि नहीं? if I sum, ठीक है, if I sum up all the moment of inertia of such small masses, small mass over here, small mass over here, small mass over here, here and so on. ठीक है, if I sum up all the moment of inertia of these small masses, it will become the total moment of inertia of the complete rod. ठीक है, it will become moment of inertia of the complete rod. Hence, instead of summation I can use integration. ठीक है, so moment of inertia for a continuous object, is calculated using integration r square dm. Is calculated using integration r square dm. ठीक है? Like let's see and let's see the example of rod only. ठीक है? You will be able to understand. It is very same. It is almost same to the calculation of center of mass only. ठीक है? Just instead of x dm, here I am using r square dm. That's it. ठीक है? There you were using r dm. I am here using r square dm. That's it. That is the difference. ठीक है? Nothing else. So let's calculate for this rod only. Suppose the length of the rod is L. ठीक है? The length of the rod is L and its total mass is capital M. ठीक है? So if the total mass is capital M, if I want to calculate moment of inertia, I will have to do what? Integration r square dm. I have to do integration r square dm. So what we can do is, ठीक है, at a distance r, I will take a very small element. ठीक है, a very small element. What will be the length of this small element? The length of this small element will be dr. Simple. ठीक है, it is a small element, so its length will also be very small, dr. ठीक है, so same as what we did in the center of mass. You know, we used linear unitary method, ठीक है, to find the value of dm. So here also we will do that only. For L length, the mass I get is capital M. Okay, for L length, I am getting a total mass of capital M. So for unit length, I will have mass M by L. Okay, for a unit length, I will have mass M by L. So for a dr length, for a dr very small length, what will be the mass I will be getting is M by L into dr. M by L into dr. This M by L into dr is basically what? This is equal to dm. This is the mass of that small length dr, this small mass over here, small elemental mass dm. Okay, so now I can do what? I can just replace these over here. So moment of inertia can be written as integration r square into dm is what? M by L dr. M by L dr. Okay, now M by L is constant, it will jump out. You have integration r square dr. Okay, let's see. Most probably it is that only. Acha, now see. No, not to calculation mistake. Just check. Acha, now see. Your r, if you see, your r is starting from x equal to 0. Okay, your rod is starting from r equal to 0, not x, sorry. R equal to 0. R equal to 0. Okay, your rod is starting from r equal to 0 and your rod is ending at r equal to L. R equal to L. So now since I am integrating this thing with respect to R, okay, the total limit, okay, the limits will be kept on values of R. Okay, so R is from 0 to L, so my limits will be also be from 0 to L. Okay, now if you integrate this, you will have M by L integration. Okay, the integration of R square dr comes out to be R cube by 3 from 0 to L, from 0 to L. So if you replace the limits, it will be M by L, L cube by 3 minus 0 cube by 3. So this is 0. You have M L square by 3. This is the moment of inertia of a rod about an axis. Okay, this is the moment of inertia of rod about an axis passing through one end of the rod. Okay, it is about an axis passing through one end of the rod. This is the moment of inertia of a rod about an axis passing through one end of the rod. Okay, if you change the axis, the moment of inertia will change. Okay, so this value you have to remember. It is not like you don't have to remember. You have to remember this, but if you change the axis, remember I don't know what happened, but something happened over here. ठीक है, no problem. It is broadcasting. ठीक है, so just write this. ठीक है, write this. That will be all for today. ठीक है, we will stop here. That's it for today. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you. ठीक है, I guess you have written this. Yeah, I'm closing the meeting.